Welcome, Algebra class. We are going over Chapter 12, Lesson 6 right now. And Chapter 12, Lesson 6 deals with, excuse me, a concept called rationalizing the denominator. Now, what on earth does that mean? You know what a denominator is. In a fraction, you have a numerator and that's over a denominator. And of course, the denominator tells you what type of fraction we're dealing with, whether that's halves or quarters or fifths or whatever, and the numerator tells you how many of them you have. So, denominator, that part of this phrase, rationalizing the denominator, makes sense. What about rationalizing? So, let's talk about the difference between rational and irrational numbers. We mentioned a while ago, you probably don't remember, but kudos to you if you do, that a rational number is any number that can be represented as a fraction of two integers. So what is an integer again? An integer is going to be basically any positive or negative number that's not a fraction or a decimal, or doesn't become one when you start to simplify it. So like, for example, the set of integers, includes 0, and then all the counting numbers and their opposites. So one simple way to define integers is whole numbers and their opposites. If I have a number like 7 over 18, that's a rational number because 7 is an integer, 18 is an integer. And if I have a number like 3.75821 over 9.77111312, that's probably gonna not be interpreted as a rational number in any situation, I would imagine. There's a small chance that when you divide these two numbers, it would result in something that you could express as a fraction of integers, but I highly doubt it. I'm not going to take the time to figure that out. But anyway, this is certainly not a form that you would use to prove that something is a rational number. You need to prove something is a rational number by making it the result, the quotient of dividing an integer numerator and an integer denominator. So, like for example, 3 over 9, that would be a rational number. And one last point on rational numbers as we're reviewing it. 1/3. What does that become when we actually divide it into a decimal? It becomes 0.3333, etc. It goes on forever. So a rational number can go on forever as a fraction as long as it can be expressed as the quotient of two integers. 1 divided by 3, yep, those are two integers, and so you have a fraction of two integers. 0.3 repeated is, in fact, a rational number. What is an irrational number? Irrational numbers cannot be expressed as fractions of two integers, as I said, and a characteristic of them will be just kind of decimals that go on forever without a pattern. For example, pi, if memory serves me correctly, is an irrational number. One thing that definitely is an irrational number that we encounter a lot is going to be, back to our topic of square roots for this chapter, square root of 2, square root of 3, square root of 5. Square roots that don't become perfect squares are going to result in irrational numbers. So, rationalizing the denominator means, in the case of this lesson, dealing with fractions, making sense of fractions, or converting them into some kind of a form that would look like a rational number. So if I have, I don't know, 3 over the square root of 7. Remember, if a rational number is the fraction of 2 integers, is this going to be a rational number? No. At least not in its present form is it going to look like a rational number. But if there's some way that I could get this denominator to not have a square root in it, then at least the denominator would be rationalized. So rationalizing the denominator refers to, in the case of this lesson, taking a denominator that has a square root and getting rid of it, turning it into something that doesn't have a square root. So let's do example number 1, which is to rationalize the denominator of 2 over the square root of 3. Our answer, I will just tell you right now, is not going to be a fraction of 2 integers, so it's not going to be that the entire number looks rational. It's just going to be that the denominator will have an integer in it instead of any irrational number. So how many of you would actually like to divide 2 by the square root of 3? Probably none of you. But if we're dealing with just a denominator of 3, that's not a big deal, right? So let's go back to our idea of inverse operations. The opposite of addition is subtraction. The opposite of multiplication is division. What is the opposite of square roots? It's squaring. So if we want to get rid of a number under a radical, then what we need to do to get it out of the radical is multiply it by itself. And if that doesn't make sense to you, you can look back at my review video on chapter 12, lessons 1 through 3, where I go over that in probably a painful level of detail. So if I simply want to get rid of this being a square root, then what do? I use the identity property of multiplication, which says if I multiply any number by 1, its value stays the same. So what form of 1 can I multiply this by to get rid of that issue? How about the square root of 3 divided by the square root of 3? Anything divided by itself equals 1. What happens if I do this? Well, in the denominator, I solve a problem, because if I have the square root of 3, you know what, I'll do this in an extra step. This is an extra step that you don't really need to do. You can do it mentally, but I've been doing it all along, so I'm going to continue to do it in case it helps anyone. If I have the square root of 3 times the square root of 3, could I not also write that as the square root of 3 squared? And I could put the squared sign inside or outside, it doesn't really matter in this case. But if you're squaring something and finding the square root, those are inverse operations, so I'm going to get rid of that, and I'm going to get rid of that. So what I'm left with then is an answer of 2 square roots of 3 over a denominator of 3. Is 2 square roots of 3 over 3 the same number as what we started with, which is 2 over the square root of 3? It actually is, yes. It's just a different form, and it's more useful because you're not dealing with a really uncomfortable square root denominator. We have a rationalized denominator. Let's move on to another problem. For this one, we have a more complex denominator, and so I'm going to have to introduce a new concept. One over 3 plus the square root of 6. How can I rationalize that denominator? Well, let me just try something, which, by the way, is not going to work. This is not the way to do it, but this is just, if I were trying to figure this out on my own, this would probably be my first thought. Can I multiply the square root of 6 by something to get rid of this radical? Yes, I could. If I multiplied this whole fraction, again, this is not the right way to do this, but this is a logical way to do it, which we'll see will not work. If I multiply it by the square root of 6 over the square root of 6 to get rid of that, what's going to happen? Well, in the top, I get 1 times the square root of 6 in the bottom, remember something, which is that every time you have a fraction, you have imaginary parentheses around each numerator and denominator. So if I multiply this by this, don't I have to multiply the square root of 6 by both? Yes, I have to use the distributive property. So let's go ahead and show that. We'll see why this doesn't produce a good rationalized denominator. Because, yes, I can multiply the square root of 6 by the square root of 6. That's going to give me just regular 6. But then I also have to multiply it by 3. So here's what I get. 1 square root of 6 over 3 square roots of 6 plus 6. Now, you could, if you really wanted to, you know, if it had been something like this, if it had been just like 1 square root of 6 over 3 square roots of 6, then could you cancel the square root of 6 out? Yes, because these would just be factors, and you could cancel them by division. But the problem is this plus 6 down there. Now this entire thing is its own factor, and you can't cancel the square root of 6 with the square root of 6 plus 6. This addition in there makes it not work. So this is not going to produce a rationalized denominator. And you might be asking yourself, well, how on earth can I take something where I have you know, a number under a radical, like a square root and a whole number? How can I rationalize that? There's actually a trick to it, and it's rather clever. It's multiplying the denominator by its conjugate. So you can whip out your math dictionary for this if you want. I'm not really going to define it, I'm just going to demonstrate it. So a conjugate the conjugate of our denominator, 3 plus the square root of 6, is going to be 3 minus the square root of 6. These are conjugates. And what a conjugate does is it's going to be a factor you can multiply your number by in order to get no square roots as your product. So our trouble before was when we tried to multiply this by, say, like the square root of 6 by itself. The square root of 6 was not a conjugate because we resulted in 3 square roots of 6 plus 6. So there was a square root in the problem. And if you multiply it by a whole number, like, I don't know, let's just say 6 for some reason, then that would give you a whole number here, 18 plus 6 square roots of 6. Doesn't deal with the square root. But this, believe it or not, will. Why? Well, let's test it out. We're going to do the whole FOIL thing. So first, and then we're going to do, I'll just do it this way, lasts, and we're going to do inner, and we're going to do outer. So FOIL, FOIL. That gives us then, should I do the square or should I do the full written way? I'll do the square first. I definitely prefer the square now. It's one thing I love about Jacobs. It gives you all kinds of alternate ways to do things. All right, so let's see if this produces, oops, 3 minus 6, I did that wrong. Let's see if this produces a product that has no square roots in it. If it does, then these are conjugates. 3 times 3 is 9. 3 times the square root of 6 is 3 square roots of 6. 3 times negative square roots of 6 is negative 3 square roots of 6. And then the square root of 6 times the square root of 6 is 6. Do we have any like terms to add? Yes, we do. Square root of 6 and square root of 6 can be added. So this gives us then 9 plus 3 square roots of 6. Oops, I'm writing this all incorrectly. Minus 3 square roots of 6 plus 6. The plus 3 square roots of 6 and the minus 3 square roots of 6 are going to cancel out. And it looks like I have more board space here, but it's not appearing on the screen, so I'm going to just write my answer up here. We end up with 9. And actually, you know, I didn't add all the like terms because these are like terms as well, 9 and 6. So 9 plus 6 is going to be 15. Our answer is actually 15. So, are there any irrational numbers in this? Are there any square roots that you can't fully, you know, result in a, or fully simplify into a whole number? No, this is purely rational. This does not have any irrational square roots. So, are these two conjugates? Yes. How do we find the conjugate of a number? We're basically going to be using that whole FOIL method we've done in the past with a plus something you want to get rid of and a minus something you want to get rid of when it comes to, well, I shouldn't say it that way. You're going to have basically like a plus a square root and a minus a square root that are opposite numbers. In other words, if you added them together, you would get 0. So then, first and last are going to be whole numbers because you have a whole number times a whole number. But then if you square a square root, that's a whole number. You're just, you know, square root of 6, square root of 6. So first and last become whole numbers. And then the middle ones produce irrational numbers. You know, with your square root, you have a 3 square roots of 6 and a negative 3 square roots of 6. But because of this plus and minus, they're going to cancel each other out, leaving only the whole numbers. So that's the beauty of the conjugates. You can use them to obliviate your irrational numbers that you don't want in your problem. So then we can apply that to fractions with denominators that have square roots. We can get rid of the square root in the denominator. Let's do this example. 1 plus, and we'll use exactly the same thing. Sorry, 1 over 3 plus the square root of 6. I think I'm going to write these horizontally for now, because I think with the fractions they'll use less board space if I do. Actually, you know what? I'll just erase this conjugate. Hopefully you remember what a conjugate is now. If not, replay the video. So how do I rationalize this denominator? I'm going to multiply the whole fraction because I can't multiply the fraction by anything without changing its value unless it's the same numerator and denominator. So I'm going to multiply the numerator and denominator by the conjugate of 3 plus square root of 6. And the conjugate is going to be the same thing, but with the square root with its opposite. So this is plus square root of 6. The conjugate will be 3 minus the square root of 6. 3 minus square root of 6 over 3 minus the square root of 6. Multiply this out, we'll have to use the distributive property. I'll do exactly what I did before a moment ago. This is redundant, but three times 3 is 9. Square root of 6 times square root of 6 is 6. 3 times the square root of 6 is 3 square roots of 6. 3 times the negative square root of 6 is negative 3 square roots of 6. When we add these together, we get 9 plus 6. We can just go ahead and add that. That's going to be 15. And negative 3 square roots of 6 plus 3 square roots of 6 cancels, so this will become, in the denominator, 15. What I get then is 1 times 3, which is 3. Well, you know what? I'm just gonna actually write this out more fully. Sorry for getting ahead of myself. This is our step 2. And I kind of did up to step 3 over there by accident. If I wanted to, well, no, I can't do that. Never mind. There. And in the denominator, we just simplified this when we multiply it out, doing the whole FOIL thing. Results in a denominator of 15. And the numerator is going to be 1 times 3. We have to use the distributive property. Minus 1 times the square root of 6. Would you rather deal with this fraction, the original one, or this one? This one's a little easier because you've gotten the radical out of the denominator. It's easier to think about dividing by 15 than it is about dividing by 3 plus the square root of 6. All right, what would the conjugate of this be? What would the conjugate of this denominator be? So our goal is, in finding a conjugate, we're trying to multiply it by something that will convert this into having no square roots. This has 2 square roots, so how do we deal with that? It's actually not going to be that difficult, because we already have a minus sign in here, so our goal is basically we need to multiply this by something that will result in this being a whole number. And then, I should say an integer, sorry, just in case you ever have a negative something or other, although it wouldn't make any sense to have a negative inside, it would be outside, but whatever. And then over here, have to multiply this by something that'll convert it into an integer as well. Then in the middle, we need to have a plus some kind of a square root and a minus some kind of a square root that'll cancel each other out. So what we need then is we need to multiply it by a conjugate of, I guess I'll rewrite this. The conjugate is going to be square root of 7 plus the square root of 3. Remember, when you're finding the conjugate, you just need a plus and a minus one of your square roots. So this should cancel. I'll rewrite this one more time. 4 times the square root of 7, just to show that we need to use the distributive property to resolve all of this. Go ahead and do my FOIL square. What we're really doing is multiplying by binomials. I'm just calling it foiling, which is not the best way to say it, but it's easier. Square root of 7 minus the square root of 3, square root of 7 plus the square root of 3. Square root of 7 times square root of 7, 7. Square root of 3 times the square root of 3, this is going to be negative 3. I want to make sure I didn't copy the problem wrong just a second. No, I did. I did it right. Okay. And then in the middle, square root of 7 times, or sorry, yeah, times the square root of 3. This is going to be a number we don't want, which is the square root of 21. But before you panic and think, oh no, I'm going to end up with a square root in there, what happens when you multiply 7 times negative square root of 3? That's going to be negative square root of 21. These are like, you can add them, they're going to eliminate each other. So what we're left with then is 7 minus 3. So just to spell that out a little more clearly, 7 minus the square root of 21 plus the square root of 21. These two are going to cancel each other out. Minus 3. What's 7 minus 3? 4. So we have rationalized this denominator, and I'm going to have to draw it up here again because the camera's aiming too high. I brought the camera closer to fix, hopefully, the focus problems we were experiencing last video. I think I also have the lighting better, so let me know if either or both still need improvement. So this gives us then 4 square roots of 7 plus the square root of 3 over a denominator of 4. And there's something really nice about this. Ask yourself, do you stop here or can you keep going? Now, I can't cancel things that involve plus or minus. I can't cancel separate terms in a fraction unless I cancel the entire term itself. So as I've said before, remember that the radical sign is like parentheses and an operation at the same time. I guess technically the fraction bar is too, because you kind of have parentheses around the numerator and the denominator, and then it tells you to divide. But that's a rabbit trail. So if I have this square root of 7 plus 3 plus the square root of 3, what I'm saying is 4 times, and then I can have like an imaginary parentheses in here if I wanted. So could I actually cancel 7 plus the square root of 3 if the entire phrase appeared in the denominator? Yes, but that's the only way. Am I free to cancel this 4? Well, fraction bar tells you to divide, and the opposite of multiplication is division. So when you have multiplication, in other words, separate factors being multiplied by each other in the numerator, then you can cancel any of them with the denominator if you're canceling the entire factor. So I could cancel an entire square root of 7 plus square root of 3 if I, oops, I wrote that wrong. You know what? I just explained the entire thing as if it were all under one radical. It wasn't, sorry, because then I was like, oh my gosh, wait a second. I wrote a square root of a square root. That doesn't even make sense. Okay, so this is how it is. Everything I said to you is accurate, except I just wrote the problem wrong, so I was applying it in a way that didn't need to be applied. Sorry about that. However, okay, so I can't cancel these terms, but this is a factor by itself. It is just 4 times something. I can't cancel plus 3 under any circumstances because it's like a plus something. But 4 times square root of 7, yes, I can cancel the 4 and the 4. And so then my answer is the square root of 7 plus the square root of 3. Hopefully you understand why I could cancel the 4 and the 4. Sorry about my really bad explanation of that. Anyway, so that's your answer. And the trick really, again, is just finding the conjugate of whatever square root you're trying to get rid of in the denominator, or square roots in the case of this problem.